Okay, I was going to refer to the picture, but I'll come back to that. Okay, when we integrate this, we're integrating p with respect to x, right? So we're integrating from here to here, and then we do something here, and so, but basically we're integrating from here to here and then from here back to here, right? Okay, the integral of p dx over c1 is approximately equal and opposite to the integral of p dx over c3. Because this is a tiny rectangle. This path is very close to this path. And if the function isn't pathological, you make it small enough that these two are practically the same, but not quite. Now, there's a very small difference. Due to what?
The change in the function value between the two paths.
Yeah, there's a difference in the function values here and here. Tiny difference, but it's a difference. Okay? What does that difference depend on? What aspect of p causes the function to be different here than it does here? Well, what changes between here and here? What coordinate changes between here and here?
I guess y.
Yeah, due to the change in y. Of course, we'll have a delta x down here and a delta y up here, right? Okay. So partial p with respect to y gives you a very good approximation of what that change would be, right? That's one idea I want you to lock in, because when we prove Green's theorem next time, at least with a little hand waving, you're going to need to understand that. Okay? P changes between here and here because it changes when y changes. So you take its partial with respect to y, and that gives you an estimate of how much it changes, right? And there you see the py, right? Okay? Now, similarly, the integral of q dy changes between here and here, or between here and here, right? Okay? And that's because q changes when x changes. Okay? In changing these integrals, I should have said the difference in the integrals, and I should have did a q dy here, right? Okay? Now, this can be expanded from little rectangles to any nicely shaped closed region, okay? And this is a closed region. R is the region that bounds the path C. So any path, well, we'll get into the details of it. What this does is it relates an area integral of py minus qx to the integral, the line integral around the curve. Okay? So it turns out that the values of p and q on the curve determine the integral of this expression over the interior. Okay? Similarly, this expression determines the line integral. Okay, so you have an area integral that's equivalent to the integral around the curve enclosing that area. And sometimes this integral is easier to do, and sometimes this integral is easier to do. Okay? There are expressions like this that you can't even begin to integrate, but when you do the partials, you get something that you can integrate over the area. And there are cases where this is just impossible. These partials are impossible to take to integrate with respect to area, but this is possible, okay? Now this is extremely profound. This is why, or how you prove essentially the symmetry of the symmetry of the gravitational field flux integrals and stuff. Yeah, we'll talk about that later, okay? I was going to say something about it, but we're out of time. So please take some time and understand what I'm telling you here. Even if you don't know the details and how to connect all this, once you get the picture, the details are not particularly difficult. Moderately, but not excruciatingly, okay?